first of all. There we go. Your fourth homework, I believe it is, and the review for exam 2 were posted last night. Homework 4 is going to be due Thursday since the exam is Friday and we shouldn't really have those overlap, but I want to give you guys the chance to practice before the exam. And so that is due Thursday. And then the exam 2 review isn't technically due. You don't have to do it, but it is just a good comprehensive overview of problems from this unit. You'll notice looking at it, there's really only 2 kinds of problems we did do in the last 2 weeks. And that is A, solving trigonometric equations, and then B, doing trig proofs. And those all use the identities page in your course packet. So if you have not found yet, that is going to be pretty much the thing you live by for both the exam and for the review and the homework. Everything you need to know should be on those. But the exam review, you technically don't have to do it. But if you want to practice beforehand and then get some feedback, we will be going over that in class tomorrow. Tomorrow will be the day we're reviewing for the exam. So that should be up under the homework category in WIO courses. Otherwise, just keep moving with the ALEKS. I know there's some assignments this week that are only open for a 24-hour window. That's because they're relatively short, but if you can't do those in that 24-hour window, remember that you will have a second chance. If you remember from exam 1, we had those second chance exam 1 topics where every single topic from ALEKS reopened from the day of the exam, that Friday through Sunday. You will have another one of those for exam 2 topics where, say, you just didn't quite have time to get all the sum difference identity problems done in ALEKS. You can go back in later and redo them. So just keep an eye on ALEKS because there are some things that are only open for a day or 2 now because we're getting into these shorter topics. So make sure you keep an eye on that and don't miss them. Any questions on anything? Charles, what's up?
I noticed on the ALEKS, there's a unit 1 thing that was worth like 100 points. Was that just doing unit 1 things? It wasn't a
do you
specific
mean
assignment?
Yeah, are you talking about in ALEKS or in the grade book?
I think it's in the grade book. It says ALEKS unit 1. I guess I'm not sure what else it says, but it had to do with unit 1.
Gotcha.
I'm guessing it just to do the unit 1 things in ALEKS? Is that what?
Yes.
Or is it a specific thing?
Yes. No, I haven't put the grades in for that yet. I'm going to do that soon. But all that is how I think it's going to be out of 104 is actually it's going to end up being out of, because there were 52 topics in unit 1, but it's basically 2 points per topic you learned on time in ALEKS. So if you learned all of the unit 1 topics by the end of unit 1, you're good to go with that.
Okay, thank you.
Yep. That's not a separate assignment. Don't worry, there will be another one of those for unit 2 as well. Because if you remember your ALEKS grade at the end of the semester, half of it is from just learning the topics, not mastering them. It has nothing to do with the knowledge checks yet. It's just from, did you go through and do the ALEKS topic before the end of the unit? And then the other half of your grade will only come at the end of the semester, and it's how many topics did you retain mastery in? And that part comes from doing well in knowledge checks, because you learn the topics when you do them in the ALEKS module, and then you master them when you test them correctly on your knowledge checks. So, and I will explain more about that towards the end of the semester, but I will put in those ALEKS unit 1's grades very soon. Okay, any other questions? All right. Well, if there's no other questions, if you remember today, we are done technically learning content for this unit. So what today is going to be focused on is I just picked 9 proofs for us to do, just to get some more practice and familiarity with those, comfortability with maybe how do I approach them, what kind of techniques am I going to see show up. So we're going to go through 9 of those, and then that'll be it for today. We will be doing more proofs tomorrow because there are some on your exam 1 or exam 2 review. Gosh, we're on exam 2. And there's also some solving of equations on the review that we'll be going over tomorrow as well. So on that note, I will go ahead and share the slideshow. All right, cool. So yeah, today we're just going to do, oh, that's annoying. So today we're just going to do a few proofs, and that's going to be pretty much it. If anyone has any questions throughout, please, please, please interrupt me. I know these can be kind of confusing at times, and it's kind of hard to mimic the process of, thinking through, because we all think differently. It's kind of difficult to think through, oh, what possibilities could we take? So if anyone has any questions or other suggestions on how we might do some of these, please interrupt me. Okay. So let's start with one that's a little bit simpler first. I want to show that the cosecant of x times 1 minus cosine squared of x is equal to sine x. First thing I should be thinking about when I'm starting proofs is which side do I want to start on? Which side, either A is more complicated, is sometimes a good way to go about it, or B, which side can I immediately see that I could apply some kind of identity to? Well, I don't really know what to do with sine x to expand it to make it look like this. So in this case, I think I want to start on the left-hand side. I want to do something with cosecant of x times 1 minus cosine squared of x. I see two things I can do right here. I could do something with the cosecant, or I could do something with the 1 minus cosine squared x. I immediately recognize for me that the 1 minus cosine squared x is the Pythagorean identity. So I think I'm going to just apply the Pythagorean identity to it and see what happens. That may not be the right way to go about it, but A, I can see that I can do it right away, and B, I see a sign here, and the Pythagorean identity will get me sines. So I think that's probably the right track. So using the Pythagorean identity, I get that that's cosecant of x times 1 minus cosine squared of x is equal to sine squared of x. It may be helpful to have your identity sheet out from your course packet to look at while we're doing this, because I can't, unlike during lecture, I can't go back and refer to the identities every single time. So it may be helpful just to have those out to be looking at. But I did this, and remember, I have to label that this equality was from the Pythagorean identity. Labeling is extremely important because you have to justify every single step of your math, because otherwise it's not very readable to someone who's just trying to read and understand your work. And that's how proofs in math work in general. You have to cite theorems. Okay, so now I have cosecant x sine squared of x. I want to get it down to a sine of x. This cosecant here, I don't really want it, and I know that I can get rid of it. I know I have the reciprocal identities to get rid of it, so I'm just going to get rid of it. So just applying the reciprocal identity to cosecant of x, cosecant is equal to 1 over sine of x times sine squared of x. This was by the reciprocal identity. Just multiplying these two things out, sine squared of x over sine of x. And then I see from that I can cancel a sine, and I get sine of x. And that's the end of my proof. There were no identities used in this step to this step because that was just multiplication. And there were no identities used this step to this step because it was just algebraic cancellation. I haven't mentioned this yet, but at the end of the proof, if you want to signify that you're done, there's two things we commonly do in mathematics. Sometimes we write something called QED at the bottom, and that's just the fancy Latin way to say, hey, I'm done. This is the end of my proof. We can write QED at the bottom. Another thing that we could do to signify that a proof is over is just draw a box and color it in. That's saying, hey, I'm done. This is the end. You'll see this in math a lot. I forgot to mention it when we first did proofs, but if you want to just write one of those two at the end just to signify, hey, this is it, I'm done, you can do that. Questions on this proof? All right, let's try another one. I want to prove that the cosecant of x minus cotangent of x times cosine of x is equal to sine of x. Once again, I want to think about which side I want to start on. Okay, I don't really know how to expand sine of x to look like any of this garbage on the left-hand side. So I think the only really logical thing to do here is to start on the left. Cosecant of x minus cotangent of x cosine of x. Okay, I know I just want to get it down to a singular sign at the end. So the only thing I can really see to do is to get rid of this cosecant and this cotangent because I have quotient identities that can get rid of those two things. So I'm just going to start by doing that. This would be equal to 1 over sine of x minus cotangent is cosine of x over sine of x. That's the quotient identity, and then we just leave the cosine of x alone. And then I have to write that this is by the reciprocal identity, reciprocal and quotient identity. I want to get just to multiply this cosine of x over sine of x by cosine of x, just to make it look a little nicer. I'm going to do 1 over sine of x minus cosine squared of x over sine x. I just do these extra steps. Sometimes you don't necessarily need the step that I just did. If you can see right away that this is cosine squared x, I just do it because A, it doesn't hurt, and B, it just looks nicer when we write things out like that. Because when I did that, I can see, oh, I have a fraction, two fractions with a common denominator. I can subtract them. Beautiful. So I'm going to do that. This gets me 1 minus cosine squared x over the common denominator of sine of x. Cool. Now I see this thing in the numerator, 1 minus cosine squared x. What did we just use on the last proof for 1 minus cosine squared of x? By the Pythagorean identity, that is equal to sine squared of x. And I have to write down that this was by the Pythagorean identity. Cool. And then immediately I can see that we have a sign cancel from the numerator and denominator that just leaves us with the sine of x. Beautiful. We are done. Questions on this one? This one used a lot of similar techniques to the first one with the reciprocal and quotient identities, then just combining fractions, recognizing, hey, this looks like the Pythagorean identity. Maybe I should try that. And then signs cancel nicely and we're done. Another way to think about it rather than just, hey, this looks like the Pythagorean identity is I want to get signs. How can I have this 1 minus cosine squared. How can I turn that into a sign of some form? And again, that also leads you to the Pythagorean identity. All right, let's try another one. We have cosine of x over 1 plus sine of x is equal to the secant of x minus the tangent of x. Okay, now I honestly, the left side to me looks a little bit more complicated. Cosine of x over 1 plus sine of x, there's a fraction there, there's a lot going on. However, I don't really know what to do with that to get it into secants and tangents. I know tangent is sine over cosine, and I know secant is 1 over cosine, but I don't really know how to manipulate that to get it to look like the left-hand side here. So I'm going to start with the right-hand side. Even though superficially it looks more simple, I know right away that I can apply quotient and reciprocal identities to the secant and the tangent in order to make it look like what I want it to look like. So I'm going to start at the bottom here because I want my final destination to be equal secant of x minus tangent of x. Now, how do I work backwards from there? Well, I know from the reciprocal and quotient identities, secant of x is 1 over cosine of x, and tangent of x is sine of x over cosine of x. Just working backwards a little bit. And I'll label these later with the steps because I'm just trying to think backwards right now. And then when I go back and read it forwards, I will label the steps with how I used them because sometimes it's easier just to label everything at the end. I see that I have two fractions here being subtracted with a common denominator. So I'm just going to combine these fractions because our final answer is 1 fraction, so why not? So then this is equal to 1 minus the sine of x over the cosine of x. This is frustrating. This really, it looks so close to what we want, except it's like the thing we want in the denominator is in the numerator, but it's a minus sine of x instead of a plus sine of x. So what we want to do here Because, okay, there's no trig identity we can apply to make it look like what we want to. There's not a reciprocal identity. We can't just flip it upside down because even flipping it upside down doesn't quite get us to where we want it. And it's not true that, I mean, this is not true. So we couldn't just do that and try to work with that. So this is the case where we have to be a little bit creative. Oopsies. We have to be a little bit creative here. If we remember, I've talked about something called a conjugate before. And if we have something like a plus b, its conjugate would be a minus b. So I'm trying to think about, okay, I want cosines in the numerator and the sine thing, and I want 1 plus sine in the denominator. So what if I multiply by the conjugate of 1 minus sine? Or at least the fancy one with the conjugate in the numerator and denominator. What if I do this? We may not see why it works right now, but I'll explain in a bit. So let's just try it. Let's see what happens. Let's see if this gets us to where we want. I'm actually going to write that in a different step though, because clarity is important. So we have 1 minus sine of x over cosine of x times 1 plus sine of x over 1 plus sine of x. Cool, what happens when we do that? In the numerator, we get because it's the conjugate, we get 1 minus or plus sine of x minus sine of x. So the plus sine of x and minus sine of x cancel, and then minus sine squared of x. Cool, so the numerator is just 1 minus sine squared of x. And the denominator, I am just going to leave b for now. Okay. What is 1 minus sine squared of x equal to? Well, Pythagorean identity, sine squared plus cosine squared equals 1. So 1 minus sine squared of x is actually equal to cosine squared of x. And you may not see it immediately, but we're actually done here. Because how do we get from here to here? Or if you want to think about it, reading it forwards like we will in a minute, there to there. Well, we just cancel a cosine from the numerator and denominator. Because if we canceled a cosine from the numerator, we just have the cosine of x left. And then getting rid of that cosine in the denominator, we just leave 1 plus sine x, which is exactly what we wanted. So we're actually done here. But why did this work? Why did multiplying by this weird conjugate, this weird form of 1 that I seemingly pulled out of nowhere work? Why did that work? Well, because this is a 1 minus sine and this is a 1 plus sine. That made those middle terms of the two signs cancel. So we were just left with the constant term and the squared term. And when we have something like that in trig, that should immediately trigger our Pythagorean identity alarm. Whenever we multiply by something like that, where there's no middle term and we're left with this kind of quadratic expression, we should immediately just think Pythagorean identity and try to get rid of it that way. The other reason it worked is because it happened that the conjugate we were multiplying by, this 1 plus sine x, just happened to be what we wanted in our denominator anyways. So that is why that worked. Okay, we're not quite done though. We have to think about labeling. From this step, oopsies, come on. Okay, from this step to this step, what did we do? Well, we just kind of multiplied the numerator and denominator by a cosine of x. No trig identities used. Cool. This step to this step, what did we do? Well, we took the cosine squared of x and turned it into a 1 minus sine squared of x. So this step was by the Pythagorean identity. All right. Now what about this step to this step? All we did there was factor out a 1 plus sine of x from the numerator and denominator. No trig required. This step to this step, what did we do? Well, because this was a 1, technically a 1 over 1, we just canceled them. They're gone. No trig identity used. What about here to here? We just pulled the fraction apart. If you think this is one uniform fraction here, all we did from that step to the next one was just pulled those two fractions apart into two different fractions. And then finally, the bottom one, we turned 1 over cosine into secant and sine over cosine into tangent. And this used the reciprocal and quotient identities. Notice this proof was much more algebraically difficult than trigonometrically difficult. We only use two identities, and they're honestly two that me personally, and I think most people get by far the most comfortable with. Sometimes it's just trying different things with algebra, using your college algebra toolbox and seeing where we can get. Questions on why this one works? Okay, let's do another one then. I want to prove that the sine of the third of x times cosine squared of x equals cosine squared of x minus cosine of the fourth of x, all difference times sine of x. Looking at these two, it looks a little overwhelming at first. We have a lot of exponents flying around here. But which side seems most easiest to work with? I don't really know what to do with these, but I see something I can factor out of that. I see a common factor. So I'm just going to start on the right-hand side of the equation. I want to start with this right here. Like I said, I can see something I can factor out. This entire quantity here is times the sine of x, and I see a common cosine squared of x that I can just pull out of there and have it go join the sine of x. So I'm going to do that. What I mean is just pull out a cosine squared of x because there's a common factor there. When we pull the cosine squared x out of the first term, we are only left with 1. When I pull the cosine squared x out of the second term, I'm just left with a cosine squared of x because 4 minus 2 is 2. And then the sine of x is still just there. Cool. Did I use any identities in any of these steps? No, but again, I can think about that later since I'm working backwards and it's a little bit harder to label working backwards sometimes. Okay, once again, our friend 1 minus cosine squared x has showed up. Hopefully we recognize by now that it's a good idea to try Pythagorean identity at this point, because we know that that is equal to sine squared of x, and we know we need 3 sines in our final answer, and we only have 1, and this is going to give us 2 more sines. So this should be an indication that we're on the right track. So that then cosine squared of x times sine squared of x times sine of x. Cool. Simplifying this more, it's cosine squared of x times sine to the third of x. Hey, multiplication is commutative. We could just swap these two around and we're done. Beautiful. Okay, so what did we do to get to this point? Well, here to here, we didn't use any identities. We kind of just separated multiplication. Here to here, we used the Pythagorean identity. We replaced this sine squared of x with 1 minus cosine squared of x. So this line we label with Pythagorean identity. And then the bottom line, all we did was multiply that cosine squared of x that was out here back through. So no trig used there. And so we are done with this one. We can draw a little box at the bottom. Beautiful. This one was not, again, very trigonometrically involved. We only needed the Pythagorean identity, but it's just about recognizing in these kinds of problems, especially where you see a lot of exponents flying around, 99% of the time, you're going to try factoring something out of some kind of sum or difference that's in some kind of multiplication. That's what you're going to try to do. 99% of the time when you see exponents above, to the second power. Questions on this one? All right, let's try working with a couple different identities. I want to prove that cosine of x minus y times sine of x minus sine of x minus y times cosine of x is equal to the sine of y. Looking at which side I should start on here, I'm pretty sure I want to start on the left. I really have no idea what to do to the right at all because it's just the sine of y. There's not much we can do to it. And I know this x minus y right here and the sine of x minus y indicates to me I might want to try some sum and difference identities. That should be the tip off there. Is looking in the argument of the cosines and sines. If there's things being added or subtracted, 99.9% of the time, you're going to need a sum or difference identity. So let's try that. Let's just try expanding this out using those identities. So just rewriting this as my starting point. Sine, oopsies. I'm going to use the sum and difference identities for cosine of x minus y and sine of x minus y to expand those two parts, those two terms. So this is going to be kind of long and messy, but that gets us cosine x, cosine y, plus sine of x, sine of y, all times sine of x, minus sine of x cosine of y minus cosine of y sine of, oh no, cosine of x sine of y, my bad. Forgot which rule I was using. And then times cosine of x. Cool. This is a mess. I don't know what to do with it yet, but I noticed that I can still distribute this sine out and this cosine out. So I'm going to do that. So this is equal to cosine of x, cosine of y, sine of x, plus sine squared of x, sine y, minus sine of x, cosine of y, cosine of x. This minus cancels out with this minus, so that becomes a plus cosine squared of x, sine y. This looks disgusting. I understand. I don't really want to mess with this. This doesn't look very nice right now. However, I notice right here, I have a cosine of x, cosine of y, sine of x. And right here, I have a minus cosine of x, cosine of y, sine of x. They're just written in a different order. But remember, multiplication is commutative, so we can flip-flop those around all we want. So meaning this term and this term are the same. This was just the negatives, so they'll cancel each other out. So what we're left with is sine squared of x, sine of y, plus cosine squared of x, sine of y. I can factor out a common sine of y from both of those two terms. And I get sine of y times sine squared x plus cosine squared x. It's our favorite identity. It's back again. Sine squared of x plus cosine squared of x is just 1 by the Pythagorean identity. So that's technically sine of y times 1 that we're looking at, which leaves us just with the sine of y, which is conveniently what we wanted to prove. Beautiful. Okay, we're not quite done yet. I can't put my little box down yet because I'm not quite done. I need to go back and label my work because I just kind of charged ahead. I got on an algebraic roll and I just kept going. So I need to make sure to go back and label my work and justify my steps. This first step to the next step, we used sum and difference identities. I'm only abbreviating because I'm out of room, but when you do this yourself, you should write them out nicely. So this was just by sum and difference identities. Here to here was just some multiplication, some algebra, nothing to label. Here to here was more algebra, addition. Here to here was just more algebra, factoring out a common term. And then here to here, we did use the Pythagorean identity. So I need to label that this step was by the Pythagorean identity. The rule of thumb for labeling is pretty much if it appears on this identity sheet, it is something you have to label. If it's just algebra, cancellation, factoring, addition, subtraction, multiplication, division, making a common denominator, multiplying by a conjugate, multiplying by a fancy one of any kind, you don't need to label that. Or even just raw computation, if you have to evaluate like a sine of pi over 2 or something, you don't need to label that. Questions on this one? This one was pretty straightforward. Once we recognized that, hey, this is probably going to require a difference identity, the rest of the proof just kind of fell out, just with some algebraic twiddling. Okay, let's try another one. I want to prove that 1 minus the cosine of negative x over secant of x minus 1 is equal to cosine of x. Again, I don't really want to mess with just the standalone cosine of x. I'm sure if I was really, really, really smart, creative, I could expand it and somehow make it look like the thing on the left. But why would I do that when the thing on the left looks much more approachable? So I'm going to start working with the thing on the left-hand side, just writing it out here. Okay. I see right away that I could use the reciprocal identity on that secant. However, the thing I want to do first, just because it's kind of bugging me, is there are negative signs in this secant and in this cosine. I don't have an idea what to do with the secant yet, so I'm going to leave it be, but I think I want to get rid of these negative signs. So if I remember, both cosine and secant are even functions. So what does that mean? That means that the cosine of negative x is just equal to the cosine of x, and same thing for secant. That's what it means to be an even function. If it were an odd function like sine, for example, that negative sign would, or that negative would get pulled out in front like that. But since we're working with even functions, we use the top version. So this means that this whole thing is equal to 1 minus the cosine of x over secant, positive secant of x, minus 1. Cool. Did I use an identity for this? Yep. This one was by the even/odd identities. Okay. Now I still know I just want to get to a singular cosine at the end. So I really don't want that secant in there now. So I think I will use the reciprocal identity on it just to make this 1 minus the cosine of x over 1 over cosine of x minus 1. And what was this by? This was by the reciprocal identities. Because the reciprocal of secant is cosine identity. Okay. Now I have to be a little bit clever here. I've noticed that, okay, maybe I want to factor something out. I'm trying to get something to cancel because our final answer is in the form of cosine. So I'm trying to look, is there something I have in common that I could factor from the numerator? Not really. Is there something common I could factor from the denominator and cancel? Also, not really. But what if we think about factoring a 1 over cosine of x, or not a 1 over cosine of x? What if I think about trying to pull a cosine of x out of the numerator? I can't technically do that. There is a 1 right here. That makes the 1 kind of angry. But if I factor out a cosine from that 1 right there, it becomes 1 over cosine of x. Because if you just cosine of x over cosine of x equals 1. So technically, what that was legal. Just pulling out a cosine of x from that first term there, factoring it out from the 1, that leaves us with a 1 over cosine x. And you'll see why that works in a second. Minus, if I factor cosine out from cosine, that just leaves me with a minus 1 over 1 over cosine of x minus 1. Now, can we see why that little bit of cleverness was extraordinarily helpful to us there? Before, there was nothing we could cancel from the numerator, nothing we could cancel from the denominator. Those two didn't really work out. But if we said, hey, I have a 1 over cosine of x down here, what if I tried to make a 1 over cosine x in the numerator by doing a little bit of clever factoring? Hey, this thing and this thing cancel out. They're the same thing. They just go away. By pulling out that cosine of x, which I knew I wanted my final answer to be, by pulling that out in the numerator, that gave me 2 identical factors that just completely canceled in the numerator and denominator. Again, it is very counterintuitive to try to factor out a cosine from the number 1. It doesn't make sense. It's not something we'd normally do. It's something that's actually kind of frowned upon up to this point. But the thing with trig proofs is how it's kind of like a puzzle. It's how can I manipulate this with my algebra toolbox to make it look like what I want it to. And we can see that these two things are equal, right? Because if we distributed this cosine back out, cosine x over cosine x is 1, and cosine x times negative 1 is negative cosine. So that is a completely legal move. It's one we're a little uncomfortable with because it's taking a whole number and making it into a fraction, which is ugly, but we already have this ugly fraction down there. So half of the battle of proofs is keeping an eye on, okay, where am I trying to get and what could I do to get there? And even if I don't know what to do to get there, how could I manipulate this equation? How could I try to make things cancel out a little more? With that being said, we cancel those two common factors and we are left with a cosine of x. There was no trig from this step to this step or this step to this step. That was all algebra. So the proof is done and I can just write QED right there. Questions on this one? Again, a little bit of tricky algebra right there with the cancellation, but sorry, there's a trash truck outside my window. I'm gonna go close it so it's not super loud. Sorry about that. Oops. Okay. Anyways, questions on this one? All right, then let's do another that uses the sum and difference identities. Let's try cosine of pi over 2 plus x over cosine of pi plus x is equal to the tangent of x. I already kind of gave it away, but we're going to probably want to use the sum and difference identities to start this, which means we do not want to start on the right-hand side. Again, I know the tangent is sine over cosine. Great. But that doesn't really get me anywhere. I don't know how the heck to manipulate it to make it look like the left-hand side. And as a general rule, simplification is usually easier than expansion. So I'm going to start with the left-hand side. I have the cosine of pi over 2 plus x over cosine of pi plus x. I'm going to use the sum identity for cosine on both the numerator and denominator. And that just gets us cosine of pi over 2 times the cosine of x minus the sine of pi over 2 sine of x all over cosine pi cosine x minus sine of pi sine x. And this was by the sum and difference identities. Cool. Now, I know I have some stuff in here that I'm familiar with. I have cosine pi over 2, cosine pi, sine pi over 2, and sine pi. Those are very nice familiar values from my unit circle, so I can just evaluate those. Let's do that. The cosine of pi over 2, thinking about our unit circle. Here's pi over 2. What is the x coordinate there on the unit circle? That's a big fat 0. So we have 0 times cosine of x minus the sine of pi over 2 is 1 times the sine of x over cosine of pi. We think about the x coordinate right there. That is -1 times cosine of x minus the sine of pi. The y coordinate right here is 0 times sine of x. And this was just, you don't have to label this one necessarily, but I like to whenever I'm evaluating trig functions. I like to say that this was by evaluation because I'm still technically doing trigonometry here. I'm not using an identity, but I am doing trig. So I just like to label that. Multiplying by 0 gets rid of this term and this term. So we are left with negative sine of x over negative cosine of x. Cool. Negatives cancel out, so just for my own sake, because I don't like looking at all those negative signs, that's the same as the sine of x over the cosine of x, because a negative divided by a negative is a positive. So those two negative signs, it's like we're multiplying by an invisible -1 out front that cancels out. And hey, sine of x over cosine of x, this is one of our favorite trig identities that we use all the time. It's equal to the tangent of x. And to get there, I used a quotient identity. And that is my proof. questions on this one? Again, this one very much just kind of fell out once we applied the sum and difference identities to it. Those identities kind of work like magic sometimes. Sometimes you'll need to use other identities where if you get something you can't evaluate, maybe you need to attack it with a half angle identity or something, which is why we've done some practice with those. But usually these ones are pretty straightforward once you realize what you need to do. Okay. We have two more, and these two are actually pretty similar. I didn't realize until I was doing them to prep for lecture, but the next two are incredibly similar, and you will see why and why that's kind of a good what to look out for, to look for when things are similar and when we can use similar techniques. So let's do the first one first. We have 1 over 2 cotangent of x times 1 minus cosine squared of x is equal to 2 cosecant of x. Now, I would honestly be comfortable starting on either side with this one, and here's why. I look at this one first, and I immediately see, oh, there's a cotangent. I could do something with that. Oh, there's a 1 minus cosine squared. I know an identity I've used about 10 times in this lecture alone that I could attack with that. But over here, I also see this 2x, which in my brain raises the flag of double angle identity. So I don't think I could get from 2 cosecant of x all the way to this nasty thing on the left-hand side. But I think I'm going to work with the cosecant of 2x first, just to manipulate it a little bit, maybe to get a better idea of where I should be headed on the left-hand side, because I have no idea how I'm going to make this turn into a cosecant. But maybe if I mess with the cosecant a little bit, I can get a clearer picture of where I could be headed, because there's only one double angle identity I could use here, and we're going to need to use it. So let's start by working backwards just a little bit. So I know my end goal is that I want this to look like the cosecant of 2x. Using the reciprocal identity, which I will label later, reading it forward, the reciprocal function for cosecant is sine. So we have 1 over the sine of 2x, just leaving the argument b for now, and that was by the reciprocal identity. I don't have a double angle identity for cosecant, which is why I needed to use reciprocal identity first to get that into a sine, but I do have a double angle identity for sine, which I know to be 1 over 2 sine theta, or not theta, sine of x, cosine of x. Beautiful. So now instead of looking for a cosecant, I'm looking for something in terms of sines and cosines, which is quite frankly a much more comfortable territory to be in usually. So I think I'm going to stop there with this one for now, because it's as expanded as I can get it. There aren't really any other identities I can immediately see that I want to apply to it. And I've gotten that pesky 2 out of the argument of my trig function, so I'm content this way for now. So what I'm going to do now is go back to the beginning and work forwards a little bit. So I've 1 over 2 cotangent of x times 1 minus cosine squared of x. What can I do with this? Well, I don't like that cotangent in there. I know I'm going to get to a thing with just sines and cosines in it at the end, so I might as well do that now. So this is equal, this is equal to 1 over 2 times cosine of x over sine of x times 1 minus cosine squared of x. Cool. And how did I do that? This move was by the quotient identity. Just turning that cotangent into sines and cosines. Okay. Now again, there's 2 things I could do here. I could just do some algebra and distribute this out, because I can do that, but I don't really want to do that because I like 1 minus cosine squared x how it is already. I recognize that it's Pythagorean identity, and I could get rid of this pesky 1 here, which is not in my answer anywhere, by turning the whole thing into a sine squared x. So let's do that. So we're left with 1 over 2 cosine of x over sine of x times sine squared of x. And this was by the Pythagorean identity. Cool. I'm just going to do some algebra in my denominator to do a little bit of simplification. just to multiply everything out. So I have 1 over 2 cosine x sine squared of x over sine of x. Now it looks like I've ran out of room here. I'm gonna have to rearrange this. Actually, this proof is done. If we can see from this step to this step, what happens? We have a sine, everything up here is multiplied, and we have a sine squared up here and a sine down here. So we can get rid of the sine down here entirely and cancel the squared here, which just leaves us with 2 cosine x sine x, which is the same as 2 sine x cosine x. So we're done. This proof makes sense. The first step, I just use the quotient identity to get rid of the cotangent. Then we use the Pythagorean identity to change 1 minus cosine squared x into sine squared x, multiplied things out to make them look nicer for us. Then used some cancellation to get us down to that step. From here to here, we used the double angle identity for sine. So I'm actually just going to label that now because I'm thinking about it. This was by the double angle identity. And then from this step to this step, we just use the reciprocal identity to turn that back into a cosecant. So this was by the reciprocal identity. This one was a little bit more trigonometrically involved. We used 4 different identities throughout. This one was a little bit less algebraic. The algebra just kind of fell out when we saw cancellations and stuff. But this one is done. Questions on this one? Okay, I have one more that we're going to do. And it's the cotangent of x times 1 minus cosine squared of x is equal to 1/2 sine of 2x. Now you may be thinking, hey, didn't you say this one was really similar to the last one? Well, it is. And if you don't see why right away, even though they look a bit different, there's a 2 here and there's a fraction, but there's not a fraction over on this left-hand side. They're actually incredibly similar. Why is that? Well, first of all, the thing I think I want to start again on the right-hand side, because right here I have this double angle identity and I don't have any 2x's over on my left-hand side. So I'm going to start by working backwards again. I want to start with working with the 1/2 sine of 2x, because I could start working with the left-hand side and it could work, and I'm sure it would work. However, I noticed that double angle identity right away on the right-hand side, and I know I can get rid of it, so I'm going to. And plus, it's not like we're working with cosines. Cosines are a little bit trickier when we're working with cosine of 2 thetas, because there's 3 different forms we could use, and we don't ever really know which one is the best form to use when we're just starting to work out. But the only thing that sine of 2x could be is 2 sine of x cosine of x. So why not? Why not start there? So we know this is going to be 1/2 times 2 sine x cosine x, which is just equal to the sine of x times the cosine of x. Cool. I don't really know what to do with those, so let's go back up to the top. Let's go back to the left-hand side of the equation. Let's work with cotangent of x times 1 minus cosine squared of x. Once again, I'm working with a cotangent. I know my answer is just going to have sines and cosines in it, so I might as well get it that way now by getting rid of this cotangent with the cosine of x over sine of x times 1 minus cosine squared of x. How did I get this? This was by the quotient identity. Cool. Now, just like the last group as well, I want to use the Pythagorean identity on this now, because I want to get rid of this pesky 1, because there are no added constants down here. So I want to try to get rid of them earlier rather than later. So that leaves with cosine x over sine of x times sine squared of x. This was by the Pythagorean identity. Multiplying those 2 things out, we just have sine squared of x cosine of x over sine of x, which, wow, we have a sine up here that cancels away, so the squared goes away, and the sine from here completely cancels, and we're left with sine of x cosine of x. This proof was not quite, but almost identical to the last one. And why was that? Well, instead of working, we had 1/2 cotangent of stuff over here. We just had the cotangent and the other stuff not in a fraction, just in the numerator. And that's because over here, we were working with sine, but over here, we were working with the reciprocal of function of sine. That was pretty much the difference between those two. And it made these steps at the bottom kind of different. But the first few steps were pretty much the same. We saw the cotangent. We were like, I need my answer in terms of sine and cosines. I don't want this in here, so I'm going to get rid of it. And then again, Pythagorean identity, it's probably, again, one of the most valuable identities you will learn from this class. You were able to recognize that that was applicable to the 1 minus cosine squared of x. Use that, and then it simplified down pretty much just like the last one. So just to make sure I'm labeling, Pythagorean identity to get from here to here. From here to here, we just did multiplication, nothing to do. Here to here was just cancellation. Here to here, we just pulled out a 1/2 and then had it times 2. Again, that would have been a little bit more difficult to think of working forwards, but working backwards, it made a lot of sense because we just had to combine them. Pulling apart in the special ways that are required, again, expanding is much, 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 much more difficult than simplifying. So it was probably good that we worked backwards there to start. But again, that didn't require any trig. And then here to here, oopsies, we just used the double angle identities. So this proof is done. Questions on this one or on any of the other ones we went over today? Hopefully this will help you a lot, both with your homework and with the exam coming up. There are a couple more for practice on the exam review that we will be doing tomorrow. I made the review a little bit equation heavy because we didn't do any of that today. So that we'll be doing a lot of that tomorrow. Again, this unit is pretty much just 2 things, solving equations and doing proofs. If you have those 2 things mastered, you are golden. But yeah, if you need any other practice with these, I am happy to help. The ALEKS is also a really good resource because it can walk you through some examples if you need. But hopefully today helped you guys get more of a toolbox for, okay, what should I be looking for when I start a proof? What should I be trying? And if things don't work, maybe what can I think about? And especially, I think the trickiest part of these for me is not the trig, but it's the algebra. Thinking about, okay, this doesn't quite look what I want it to look like. How could I simplify this? How could I maybe do some kind of weird factorization that I wouldn't normally do to get it to look like what I want it to look like? Or like when we had to multiply by the conjugate to make it look like what we wanted to. That was pretty difficult. But honestly, the hardest things about these for me is the algebra. So if you can master that and just get more comfortable working with the different techniques, which the best way to do that is practice, you will be set. Okay. I don't have anything else for today. I will stick around if anyone has any questions or wants to go over anything. But otherwise, happy studying. This is just take the extra time to go work on your homework. And we will be doing exam review tomorrow. No class Thursday, but I will be available via email as much as possible. And then no class Friday for the exam. All right. Have a fabulous Tuesday, and I will see you all tomorrow.